Our next example comes straight out of the physics canon, and that's the study of terminal velocity, or the velocity of falling objects. Now, one of the interesting things you can look at in physics, if you take the naive approach, is to say acceleration at the surface of the Earth is given by 9.81 meters per second squared. It's math class, so 9.8 is good enough. And what that tells us is, in principle, if we just knew that single fact, if we dropped an object from high enough, it'll accelerate and keep accelerating until it gets to whatever speed we care to think about. Now, what that would mean is if you dropped a penny off the CN tower and did the usual physics calculations, acceleration to velocities, you would be going at, well, not you, the penny would be going at 280 kilometers per hour. Think of that compared to what speed you drive in the 401 and go, that's pretty fast for a penny to be moving. If a penny hit me at 280 kilometers per hour, it would hurt. Now, I'm not saying if you drop one off the CN tower, it still wouldn't hurt, but that seems pretty fast. It gets even more dramatic if we drop something out of a plane, because what that would predict, if all we knew was the acceleration due to gravity, is that an object dropped out of a plane would be going at twice the speed of sound. So if anything fell off a plane, it would hit the ground at Mach 2. Now that starts to seem really implausible. We know that doesn't happen in general. We had to work really hard to get speeds like that when we design airplanes. So what else is happening here? We have to have something else in the mix to explain this. And of course, the resistance that we see, or the reason we do not see crazy fast speeds of falling objects, is because the air that they're falling through resists the pull of gravity. There's some extra contribution of air acting on the objects that is above and beyond the force of gravity applied. And in particular, if we look at the object and did a sort of force diagram thing, we're not going to go into detail here because not everyone's in physics, but get the gist of it. Gravity is always pulling downwards on the object. We all feel that all the time. When it's falling, it acts as an accelerant, but the air resistance is going to resist the motion of the object falling. And one of the most typical models is to model this air resistance as proportional to velocity. So in other words, the faster you go, the more air resistance there is, and it's linear. If you imagine running or cycling, the faster you go, the more resistance you seem to feel from the air. That's the kind of effect we're capturing here. So if we make that assumption that the air resistance is proportional to velocity, what we can do is come up with a differential equation for the velocity of a falling object. So we have F equals ma. That's our classic Newtonian forces. Sum of forces would be better in this case here, because we have a few. And remember that acceleration is the rate of change of velocity with respect to time. So our forces, actually let's treat it as positive. Let's say the positive direction is down. That's simply because we want to talk about velocities getting bigger and bigger, even though they're aiming downwards. Bigger being downwards makes sense from this particular context. So our sum of forces would be mg, and that would be our one force. And then we'd also have minus a constant times the velocity. So these are our two forces. This is our gravity force, and the air resistance is acting in the upwards direction in this case. And that would equal our mass times acceleration, which is dv dt. Well, that is a pretty good equation. Let's actually write it, though, a little bit differently. We're going to cancel our m's, or divide through by m. Cancel. Divide through by m, cancel. And then we have an interesting feature here. Let's see how that plays out when we write it out in more traditional form. We're going to have g minus k over m v. All right, so that is a lovely differential equation. We can do a little bit more analysis with it. In particular, we can do one of our early checks on, does this make sense? Find the equilibrium velocity. So in other words, a velocity at which the velocity remains constant. Or, what does that mean? The derivative of the velocity would be zero, or zero acceleration. If we have that type of scenario, then this would be our result. At equilibrium, the derivative is 0. We merely have g minus k over mv. And what does that tell us about the velocity, which is the thing we're interested in? That our velocity, we bring it over, let's do it in 2 stages. K over mv is equal to g, or v is equal to m over k times g. Now this is actually a nice result to get at this stage, because this tells us something that matches our intuition. When we drop a feather, we see it float. When we drop a bowling ball, it seems to move very quickly and seems to be somehow more subject to gravity. Now, any physics person will tell you it's not that gravity's changed, it's something else is going on, and it's the fact that this acceleration term due to the air resistance ends up, when we isolate out the m's, having an m in it. The bigger the mass of the object we drop, the higher the velocity at equilibrium, or what we call the terminal velocity. So mass does play a role in how fast an object ends up moving in the long run, but only if there's air resistance. It's not a feature of gravity, it's actually a feature of the air resistance when we solve these equations. So heavier objects do seem less subject to gravity, if you want to put it that way, but it's only an appearance. It's actually the fact that they have less air resistance as a net effect with mass, or proportional with mass. The other thing, of course, the more bigger gravity is, the faster our terminal velocity. So on Earth versus the Moon, terminal velocity would be higher. And there's a k here, which has something to do with surface area. Okay, so we can learn a fair bit about falling objects and the terminal velocity just from this equilibrium analysis. Before we go and find the solution, let's take a quick look at a relative analysis of some rates of change if we were going too fast or too slow relative to that equilibrium velocity. Let's remember our differential equation boiled down to g minus k over mv. If we have an object that's traveling slower than equilibrium, so that means a small velocity here and proportionately a bigger gravitational constant, so this is the same, but we have a relatively small velocity, then this whole term here will end up being positive, big minus a smaller number. And so this tells us that the object will accelerate. What does that mean for us? Well, if we take an object that's not moving, say, and we let go of it, yes, it will have a positive dv/dt, it will accelerate, and it'll continue to accelerate until it approaches its terminal velocity. However, if we had an object, say like a gun or a bullet from a gun, in that type of scenario, we could be moving very, very quickly at first. So this term is bigger. And if this term is bigger, then we end up having a negative sign overall for this whole thing. And that means that if something was going too fast, the air resistance would actually be faster, or sorry, the acceleration due to air resistance would be more important than the acceleration due to gravity. And even though the object might be falling or moving downwards, the object would, I have to be careful with words like this, but it would be decelerating or accelerating in the positive direction, or accelerating in the negative direction here. It would slow down. That would probably be the best way to talk about it. The object would slow down if it was moving too fast, because the air resistance, which scales with velocity, if the velocity gets too big, we go too fast, the air resistance builds up so it's actually stronger than gravity, and we end up slowing down. So that again describes quite nicely what our intuition would tell us about falling objects. All right, finally, let's do our classical mathematical analysis here. We've got a differential equation, let's get a solution. We've got g minus k over mv, and again, remember that these and these are all constants. As the object falls, its k and its m do not change, and the constant of gravity doesn't change too often either. So we can just work directly with this. What are we going to do? We're going to separate. We're going to separate, and so we'll have, this is all mixed together in a sum. Pretty much the only way to do this is to bring the entire right-hand side down and bring the entire left-hand side bottom up, and that would give us this form here. That's about all we can do to make sure we've got a good separation of the variables here. Once we've done that, then we can go and do our usual integration step. Integration, there we go. So right-hand side, let's actually leave some room here. The left-hand side, because v is the only variable here, it's going to be a nice ln. But we have to be careful. There's a negative k over m in front of that. So there's going to be a negative k over m that we have to divide by when we do this integral. Other side is simply t, and we have two integrals. We'll put a constant on the right-hand side to account for that plus constant on both. All right. Next, we're going to have to solve for v, because we want to know how fast am I going at what time, given all the parameters in the model. Let's take a look. Let's get rid of the k over m, bring it up. So we'll have negative k over mt minus k over mc, and next step to get to the velocity is to exponentiate. We need to get rid of that ln. And so e and the ln undo one another. And on the right, we can break that into two terms. We have an exponent with a subtraction in it. We can treat that as a multiplication down on the main line like so. And we're still honing in on v. We can now do our usual trick of let's define a new variable that sort of blocks all this together. E to the minus k over mc. And again, plus or minus. I'd like to get rid of these absolute values at the same time. And that gives us a e to the minus k over mt. There we go. Last but not least, we still need to solve for v. We're getting closer, but I think the easiest way to do that is bring this term over here, this term over here. So we end up with g minus a e to the minus k over mt equals positive k over m v. And so our velocity is m over k, invert that guy, g minus m over k a e to the minus k over m t. And if we like, we could group all of this together and let b equal that thing there. We'll just call it that big constant b. Okay. So the solving procedure is identical to what we would have seen before. There's nothing really new there going on at all. What does it mean, though, in terms of the behavior of this whole thing? Well, let's take a look at the next page where we can do a graphical analysis. If we try to sketch graphs of v of t, so t and velocity up here, what we found was there was an equilibrium velocity, which was k over m times g. And if we started at that velocity, it would stay there forever. Sorry, m over k, my apologies. M over k, that was our equilibrium. And if we started slower than that, we would speed up until we reached that terminal velocity. If we started faster than that, we would slow down until we reached our terminal velocity, and all of these solutions would look similar. They'd all have the same exponential decay flavor to them, and we can actually see that in the previous slide. We had this exponential decay and a shift, so exactly the same form if we go back to the drug model and to the heating and cooling model. All completely different sources that give us fundamentally the same kind of differential equation and the same kind of solution. So again, the mathematics we're seeing here applies in a wide range of fields, and we get similar kinds of predictions out of completely different sources for models, which is a fascinating way to see the tie-in of mathematics to those various areas.